Good morning, everyone, and welcome to our first of three multi-physics webinars in a series that we put together for you. There is a fourth webinar at the end of this as well, which we'll go into. So just to give you a little bit of background into Technia, we're based obviously here in the UK, but we have a global reach. So if there are parts of your organisation in other parts of the world, then we do have the capability to cover those for you, and it's something that you could talk to us about from that point of view. So as you may or may not know, we are a Dassault Platinum partner, and basically what that means is that we cover all of the technologies that Dassault offer, including SolidWorks now as well. But as you know, we are going to be talking around the products within the Simultaneous brand, which is the simulation brand of Dassault. So all of the technology that we're talking about is inside that portfolio, along with Abacus, which I know a lot of you are familiar with. So here's the three webinars in the series of multi-physics, as I mentioned. So today is the XFlow one, where we're going to talk about an overview of the technology and what it can do. And then obviously on Thursday, Audi, my colleague, will be hosting the electromagnetic webinar with CSC, and then we move on next week to the SIMPAC, the multi-body dynamics solution that we have. And then the last in the series, which is looking at, we've labeled it IP walking out the door. So basically it's looking at the kind of IP, not in the products themselves, but actually in the individuals. So people who have, you know, a lot of experience in FEA or engineering in general, a multitude of those techniques and experiences aren't written down. So we're going to talk about how potentially we can sort of document and record some of that sort of black art in not only in simulation, but in engineering terms and just generalness from that point of view. And then look to see what kind of areas that we can help you with through the Simulation Centre of Excellence, with some training, some online stuff, and some other things. So I won't spoil that. The reason we're doing these webinars is Dassault have introduced some multi-physics offers. So for people who already have Abacus, our existing customers, then the offer basically is if you take on one of these multi-physics packages, there is up to a 50% discount. If you get excited and want to take on a second, then the second one comes in at a 60% discount. If you don't have Abacus, if you're new to simulation, then obviously we have some introductory offers to introducing Abacus, and then the same discounts for the first and second multi-physics packages then apply thereafter. I'd like to introduce our guest presenter today. So it's Santiago from the XFlow R&D team. I won't go all through his profile, but you know, a very experienced individual, and Santi's going to take us through the XFlow presentation. So if you just bear with me while I just put him onto speaker and then swap the presentation over, and then Santi, take it away.
Thank you for the introduction. Yeah, first of all, I just want to apologise. I've got some issues on my laptop, so Matt is going to be controlling my presentation remotely. Yeah, it's a pleasure to speak with all of you. In this webinar, what I'm going to be doing, I'll be going over probably the key features and advantages of XFlow, some detail of the most recent developments that we've had over the last year, and to conclude briefly, go over some applications for various industries. Yeah, probably before starting, perhaps it's interesting to show XFlow's position inside Simulia's fluid solutions. So currently Simulia offers three products to solve fluid simulations. The first one is the Fluid Dynamics role that is directly embedded in the 3D Experience platform. And then on the right, we have PowerFlow, which was acquired with shortly after XFlow was acquired in 2017. And then finally, yeah, we have XFlow, which is the product I work on. And actually how we're positioned in this slide is quite nice because, well, I like to say that we produce the same high quality results like PowerFlow is known for, seeing as we're both based on the Lattice Boltzman scheme. And we also have a very friendly user experience, which is perfect for the less experienced users. And this XFlow is also plugged into the 3D Experience platform via the Powered by solution. So it's also got the benefits of the Fluid Dynamics engineer role on that side as well. So yeah, now if we go directly into XFlow. Okay, so yeah, unlike traditional CFD tools, XFlow is based on the Lattice Boltzman method, and it uses a fully transient approach, which means that you can directly simulate time-dependent cases. For modeling turbulence, we use an LES turbulence scheme, which is widely considered the most precise way to approximate turbulence without obviously directly solving it. So what we have is that we end up with a very competent base on which to solve a single fluid, and that same base is also available to simulate two fluids simultaneously with our multi-phase solvers. Okay. Low pre-processing efforts. So for the pre-processing side, our approach is very competitive both in time and simplicity. We have a measureless approach that consists in a lattice that is generated automatically and that only requires a user input for the size at which we desire to resolve the problem. The graphical interface, it's modern, it's simple, and it's easy to use, with a minimum number of parameters to set up to actually run a simulation. And perhaps the last is one of our most handy capabilities, is that geometry complexity is not an issue. Our meshless approach and how we treat the wall allows us to work with very complex and detailed geometry without having to add any simplifications. Now, yeah, capable of handling motion naturally. So if we move on to probably the workflows where we definitely stand out from the rest of CFD codes are the simulations that require moving parts. Again, thanks to our wall treatment, having moving parts does not require any more complexity apart from establishing the actual motion to the object through the graphical interface. And yeah, this year we released a full two-way simulation interface with SimPack, which allows us to directly simulate cases in CFD that receive a motion that is complex enough to require a multi-body simulation to actually model it. I'm going to go a bit more into depth with this in the next slide as well, but also adding on to the coupling side, so FSI, fluid structure interaction. We also do this via co-simulation, so we also have a two-way coupling scheme with Abacus to perform fluid structure interaction cases. This is another workflow which is normally tedious and is time-consuming to perform in standard CFD codes, but thanks to our approach, the fluid dynamics side at least, it's very simple and fast to set up, with the co-simulation engine orchestrating a fully automatic process. And finally, GPU enabled. So I'm going to explain that more into detail as well. But GPU simulation is considered the next big thing, or maybe perhaps not anymore because we already have it available since last year. So it turns out that thanks to the massive parallelization capabilities of the Lattice Boltzman method, the runtimes of our GPU solver are ridiculously improved, which you'll see further on. So maybe just to conclude on this slide, I normally like to summarize it in the following way. So XFlow is normally received in different ways depending on the user. So an experienced user that's been battling with traditional CFD schemes using the Navier-Stokes methods simply loves it thanks to its ease of use, minimum pre-processing time, and the possibility of simulating physics and complex cases with the detail and realism that before simply either it wasn't possible or it probably wasn't even worth attempting, okay, because of the runtimes or the complexity to actually set up the actual case. And then on the other hand, when we join a user that hasn't been too exposed to fluids modeling in the past, they normally grasp the easiness and the fast learning curve that comes with XFlow, thanks to the ease of use. And instead of getting the usual initial resistance that comes when adopting or learning a new technology or tool, you normally see that these type of users manage to extract high value very fast. So just to describe our co-simulation method, which is what I want to go a bit more into detail with, we currently co-simulate with Abacus and SimPack. So when you perform a co-simulation, a region needs to be defined where the information is going to be shared between each code. And yeah, this is the only requirement and extra setup effort that is required for these type of complex cases, which actually in XFlow, what is required is that you just simply switch a button in the GUI to do this. Then what we have, which makes everything a lot more easier and handy to operate, is that we have the cross-simulation engine, which orchestrates the entire process and takes care of the communications between each codes for each time step at this cross-simulation interface. Okay, So if you look at the diagram below, you'll see that how the iterative process that takes place automatically for each time step occurs. So what we do is that XFlow estimates the fluid load on the FSI component, okay? And XFlow will send the loads to the structural or MBS solver, which in this case will be either Abaqus or Simpac. Abaqus and Simpac will receive these loads, and then they will deform and displace the geometry accordingly, and then send this information back to XFlow. So then XFlow will receive an updated geometry with a deformation or displacement, and then XFlow will perform another iteration on this updated geometry. And that's all to it really. It's just setting one change, so one setting change in the GUI, click and run, and the customization engine takes care of everything else. So I brought two examples, one for each coupling method. So, well, this one's quite old, you might have seen it before, but it still remains one of my favorite ones, and it corresponds to an aircraft high lift stowing device. Okay, so here the FSI geometry is the rubber seal that you can see on the videos on the right hand side in black. The function of the seal is to prevent air entering the region between the flap and the main plane. And yeah, this would lead, if a lot of air leaks into this region, you'll get a drag increase and an overall decrease in the efficiency of the wing. So this system is perfectly modeled in a very simple way, thanks to our moving part schemes for the slat and the flap. The main plane is remaining fixed, and then we have the customization with Abaqus, which actually models the rubber seal that the flap moves and presses against the walls of the main plane, and that seals off the region perfectly, which you can see in the videos, and it prevents air entering. Again, normally when I show this, a lot of people see immediately, at least people with a lot of experience in CFD modeling, that it's a really complex thing to set up in traditional CFD tools. And again, thanks to how XFlow is built and the customization engine, it's a very simple thing to set up in XFlow. If you can move on to the next slide, Matt, I'll show the Simpac showcase now. So here I've decided to show vehicle water wading, which is another application that we're very strong at. And thanks to the coupling with a multi-body simulation software such as Simpac, we can add a slight touch of extra realism by modeling the full suspension kinematics and the water that actually slows down the vehicle when it enters. And actually, you can see how the chassis of the car or the body, it lifts up because of the force of the water when it wades through. So yeah, on the video on the left, you can see I'm not showing any fluid side. I'm not showing any graphical representation of the fluid, just the car entering the actual tank. Okay. So what you can see here, you can see probably, this might be a bit complex on this video and the refresh rate, but you can see that the front of the car is slightly lifted up because of the force of the water lifting the car up, and you can see how the suspension is working when the car enters and leaves the actual tank because of the ramp, especially in this position here now. Okay, and yeah, on the right hand side, what I'm just doing, I'm actually showing what the fluid is doing, the fluid side. You can actually even see on the left how the car is being slowed down by the force of the fluid again. And yeah, just to go back on the right hand side, sorry, you're seeing the actual graphical representation of the fluid markers, which are coloured with velocity, so you can actually see what the fluid is doing. So yeah, they're the two examples. I think, well, it might not suit exactly the applications of all the audience, but it gives you a very good idea of how powerful and how easy it is to get these cases working in XFlow. Yeah, so just before entering some example applications, I'd like to share with you probably our most important development over the last years, which is the GPU version of XFlow with just a general overview. Okay, so yeah, like I said, we've been developing this for a few years now. It's not something that we're just about to release. It's already been released since last year. And yeah, I don't know if you're all into GPU, but if not, I'll explain to you more or less a bit of the advantages and of the technology and how it actually fits in really well with XFlow. So yeah, this game-changing technology, what it's doing, it's cutting simulations that took 31 hours before down to 40 minutes with the same physics that we had in the standard version of XFlow. So we have the same solver as before, just working on a GPU infrastructure, and it's giving the same accuracy as before. Okay. The GPU version of XFlow is actually so fast that you can actually see design changes live in real time. In the video on the right, we're we're seeing it was recorded in our office. What we're doing is our developer is actually post-processing real time while the simulation is actually running. So if he wanted to, he could actually see live visualization of design changes on the actual design. Okay. Adaptive refinement. Okay, so we have an adaptive refinement scheme that allows you to dynamically refine the wake in an automatic way by defining a vorticity threshold on which to refine them. Okay, we can also use this to track and refine moving parts that are moving out through the domain, and that is now supported on parallel distribution, which means that you can run this, you can scale these cases on multiple project cards. Okay. Yeah, just to give you a rough idea on figures, we've seen that it can be 40 to 80 times faster than a normal CPU simulation run on hardware of the same cost range. Okay, so it allows you really, what this is, the XFlow GPU version allows you to have a HPC performance on a workstation. Also, the technology is also greener, which means that we're getting around 100 times more calculations done with 1 watt than with a CPU. So yeah, less power consumption means less heat, which also leads to less cooling. So the overall energetic impact is also much lower. So our vision on how our technology can have a huge influence on industries and organizations perform CFD simulations is the following. So if you think of it, our GPU solver would allow you to run between 40 to 80 different designs against the CPU architecture of the same price. Okay, or you can look at it at the other side of the equation. So what we've done now is that each GPU run is about 40 to 80 times cheaper than before. So the message we're trying to get through is that we would like to allow you to perform full unsteady simulations with an LES turbulence scheme, which I think many of you are going to agree that is probably one of the most precise approaches to model fluids in a very fast and cheap way. Okay, that's the sort of vision that we have with this new technology that we've developed. Just to go over quickly the development roadmap. So yeah, single phase flows and multi-phase flows are already available in the latest build. We're currently working and validating the GPU moving parts solver, which we expect to release by the end of the year. And the next milestone is to be able to have a full FSI support. And this is targeted for the first quarter of next year. Just to give you just the latest feedback of some of the customers that are using this and are seeing our results. So we've got a F1 customer in the UK, which we've done a case for them. It took 23 hours to resolve on 112 cores. Okay, they now decided to run it on an NVIDIA GPU card that we have in the office. It's if I remember correctly, it's an NVIDIA GTX. It costs on Amazon around £4,500. Okay, so that calculation that was 23 hours and 112 cores on one GPU card that costs £4,500, it only took 2.5 hours. Okay, so that shows you the run times and the performance gains behind this on very cheap architecture. And I like to sort of look at the bigger picture than this. So, okay, simulations that were taking, 24 hours are now just taking 2, which that's very good, but let's take a different view. So, in my opinion, XFlow has always been a boundary pushing tool that enables simulations that before were possible, either because of the complexity, because the physics weren't there in the traditional schemes. So what if we can now start performing simulations that weren't possible before, like probably, 20-day runtimes? You'll be very lucky if your manager lets you run something for 20 days. So what happens now if we've actually converted these impossible runs, if we convert them to overnight or weekend ones on an architecture that is cheap enough for a small company to purchase? So this, in my opinion, is the actual game changer with GPU. Yeah, one of the keys of XFlow is that it's a multi-industry tool that is targeted at many different workflows. So we're on to code that is fine-tuned and developed for just one industry. So I like to say that we're a code with robust physics and a method that works for a very wide range of applications without any fine-tuning required. So yeah, here we have some examples for the transportation and mobility, and probably 2 world-class accuracy applications we have is powertrain lubrication, where we accurately model splashing, torque prediction, and forces within the actual crankcase, and also tank sloshing. Okay. On the right-hand side, we have more civil engineering applications, where we have interior HVAC, where we recently had a very popular story that was over the news, where the 2, you've probably seen this, but maybe the 2 campaign hospitals that were built in 2 weeks in China, in Weishishan, They have a ventilation system that was designed with XFlow, so that is a key success story for HVAC. We also do building aerodynamics, loading on bridges with our multi-phase solver. There are other civil applications. Aerospace is another sector where our capabilities are highly appreciated. In this case here, the stability of a UAV is evaluated through our moving part scheme. This allows the UAV to freely interact with the airstream thanks to a built-in rigid body dynamic solver that we have. Again, life sciences industry, another very strong industry that we're gaining many cases now in the last year. They seem to be adopting a lot more simulation than they did before, and XFlow really fits in well here because many of the users are quite new to simulation. In this case here, what we're showing is an aortic valve, and again, thanks to the simulation with Abacus, we're performing many of these cases with a very high success rate. Okay, and it's always very nice to work on these type of cases. So valves and mixers, industrial equipment, they're another very common application thanks to our moving part scheme, sprays as well. Underneath we have the household applications. So we probably have nice examples, but getting the toilet to flush correctly, it's not as easy as you may think, and especially to model it correctly in CFD. Pumps as well is another application that we're strong at, again thanks to the moving part scheme. We have marine and offshore. We've worked on devices that help collect waste in the ocean. So that's a startup in the United States. You probably heard of it, the Ocean Cleanup startup. They use XFlow to model the actual devices that are thought to pick up waste in the ocean. Offshore structures, again, a very common case. We also do we evaluate ship stability, again thanks to our moving part scheme. You can see here the ship stability validated on the left bottom video. We also do sailing maneuvers, which you probably saw in the first slide as well, and some examples from the energy industry as well. So wind turbines, where we can do from the actual aerodynamics of the rotating blades to actually see internally the lubrication of the drivetrain with the multi-phase solver. Loading on solar panels. So I think that, these last slides illustrate perfectly that we're a multi-industry and multiplication tool. And I think that's about it. I hope I've stayed well in the time.
Brilliant. Thank you, Santiago. Once again, thank you very much for attending. That's all. Take care.